All right, thanks very much for coming along this evening. It's really good to have a good turnout. Right, just move along. So I'm Nicola Telchik. I'm the Vice President of Engineers Australia UK, and tonight we have Anthony Fernihough here, who's kindly agreed to give us a presentation on the water management of TfL structures. Anthony is a chartered engineer with the ICE and civil engineer, for those who are interested. And Anthony has been the head of profession over at TfL for pumps and drains for almost 8 years, previously working for Atkins on some fairly high-profile projects. And in the meantime, pretty senior over in his local rugby club, looking after things, yeah. So without further ado, Anthony.
Hi, good evening, guys. So Nicola sort of covered what I was going to talk about in the first slide. So we might as well move on, but I'm going to talk to you about water management on structures, particularly at TfL. So as Nicola said, I worked for 8 years. Over the last 8 years, and previous to that, I did a lot on waterproofing of structures during the Metronet era as well. And during that time, I came across good practices, bad practices, and okay practices. So the idea of today is to go through, one, what we do at TfL now and why we do it, and demonstrate some issues that we already have and what we've been working to over the last few years. So, and the aspiration at the end is to get, obviously, the perfect, good working example of a watertight structure. So, TfL first. What is TfL? For those who don't know, Transport for London manages the London transport issues around there. So we do tubes, London Underground obviously, we also have the buses, the cabs, London Overground, the trams, the bicycles, the walking routes, and something else which I always miss, but I can't remember, cabs, taxis, and other areas of TfL. So there's lots of those. Now on that picture you can see lots of examples of that, and that's meant to show boats. I think Nick just shouted out as well. So boats as well. So I think we've got a number of boats that go up and down the Thames and move people around. Statistics. When you look at TfL, statistically, what do we have? We've got loads and loads of statistics. So it's 23 times smaller than Network Rail, London Underground. But we carry more people per day. So that's significant. 5 and a bit million people is our peak. 5.3 million, I think, is the record. Over Christmas, sort of before Christmas. We manage the largest bus fleet in the world. There's 9,300 buses managed through TfL. So it's a significant amount of infrastructure there associated. Cycle trips are up by 154% since 2000. So we do a lot to look at cycling around London, moving people around London on bikes. And that's either the hire bikes that we have, right the way through to personal bikes. London Underground has seen a 34% increase between 2004 and 2014. There are loads of these statistics. When you look at that, the Underground is massively gaining passenger numbers every year. It's slowed down the last couple of years, but actually it is moving up again as London grows. London is constantly growing, and therefore our infrastructure around the tube particularly is growing. Obviously Crossrail, we won't mention too much about Crossrail tonight, but Crossrail is obviously going to add 10% of our capacity overnight when it comes in. We'll see. Quick other statistic, 58% roughly of the Underground is above ground. It will change when we bring Northern Line extension in, and it will turn to about 58% above ground. So we have large amounts of overground structures. Nick, head of structures, is sat in the audience, so he will obviously tell you what's going on in that environment. Below ground structures, we obviously have a large amount of below ground structures that we have to manage and maintain. They're over 155 years old, some of them, and therefore the maintenance of those and the control of water around those, which is obviously the talk tonight, is quite significant for us to investigate and manage and maintain. Another last statistic just to throw out there, by 2040, 80% of the journeys in London will be by public transport. And you can see from the roads and what we have that we have to move more to public transport. It's a more sustainable way of moving, and that's the aim of the Mayor, the aim of the mayoral transport strategy, to move people onto public transport and drive that. Water management and climate change, obviously around London, obviously when you look around Europe, Naples 2012, significant flooding in Naples 2012. Prague has suffered significant flooding in the recent years. There's been loads of flooding incidents around London over the last, around Europe in the last few years that have affected what we do and how we behave on our transport network. Sandy in New York basically Storm Sandy hit in 2012, caused multi-billion pounds worth of damage. We've had lots of work reviewing our flood risk on the underground to understand what the issue would be if we got hit, not with that size storm, but even a 1 in 100-year storm, how we respond to water main ruptures in London. So if you look at London, our biggest risk to the underground, from a flood risk point of view, 63% of our risk is associated with water mains. So how do we protect our tube against water main bursts? So we obviously work very closely with Thames Water and the other water companies in London, understanding what they do with their network and how they manage that. So some of the water management stuff isn't quite as obvious as just waterproofing, because actually we have existing structures which aren't what we call passively protected. They aren't above the water flood level. So we have to look at them and work with the other utility companies and understand that. Climate change over the next few years is obviously taking effect. I know Mr. Trump doesn't believe it, but we do. We obviously design our new infrastructure for it. We also need to review how our existing infrastructure is behaving. So, history of water management. King Canute. I think it's 1016. Everyone will have probably heard the myth that he went down to the sea and said he could stop the waves. It wasn't quite that. He didn't have that myth. He tried to demonstrate that he is only human and therefore he can't stop the waves. You know, water gets into our lowest point and it will go the path of least resistance. So as engineers, our responsibility is to make that hard for water to get in and encourage it to go where we can control and manage that. So throughout this talk, I'll be talking you through different ways that we manage water. It doesn't mean that one way is bad. Different projects have different requirements and different ways of managing that water and moving water around either the station boxes, the tunnel systems that we're working in, to basically control and do that. Because actually stopping water doesn't work very well. We can't stop it because it just comes into the next weakness and then you come back to where you started. It costs a lot of money to try and stop it, and we just persist in basically grouting and doing things that we don't need to do. So going back to London a little bit more, there's a great picture the EA sent me a few years ago, which is the Thames barrier on the bottom, running on a surge side, holding back the water from central London. So we're protected by the Thames barrier in London, and a lot of our infrastructure is protected by that. It was basically operational since 1984. Hull is designed to last originally up to 2050, but actually they've extended it to 2070, and they're reviewing some of the defence to look at how we can extend it to 2100. It is, and it basically works on a standard barrier that lifts, drawing tides. We had a wander around it a few years ago. It's a very impressive structure. The redundancy is on a sort of around roughly 6, so there's 6 hydraulic rams for every one that's needed, and so on. Impressive structure, definitely worth having a wander around. It's water management on a massive scale. You know, this was a massive thing. I can't remember, I think it's, if they hadn't have built the barrier, there's something statistic that London would have had significant flooding 19 times in the life of that project. So that would have made massive difference. And obviously, as the climate changes, the barrier becomes even more essential in what they're doing. They're also playing with the barrier, and when I say playing with it, they're using it slightly differently. So they're using it not just in surge events, but also during storm events to look at the hydraulics and how they can move water in the Thames estuary to prevent flooding in locations and move it to different places which are more resilient. So the Thames Barrier is interesting. On a bit more local scale, I'm going to talk next about TfL, or LU particularly, and the waterproof requirements. So in LU, we have certain waterproof requirements. So when we're building our below ground structures, we start looking at waterproofing. And waterproofing generally comes in at the end of the project, which is a bit late, and we're always having this battle of what comes first and who does what. We have standards. Those standards look at waterproofing and talk about waterproofing. And we have a constant argument about what those standards mean, because it doesn't matter how you write them, somebody will find a hole how to get through to it. So S1064 is the waterproofing standard for LU. With that, it basically says you have to have grade 3 waterproofing throughout our box or our below ground structure. So to BS 8102, we need to design a grade 3 structure. Now, what we also say in that standard is we need to understand what types of waterproofing we're using. So that in 8102, there are 3 types of waterproofing. And we say, to get the grade 3, because that's not prescribed by standard, we need 2 types which are different waterproofing. So A, B, which A, B or C. We need an A and a B, a B and a C, and different iterations of that. So A being protective barrier, C being structurally integral, so waterproof concrete and so on, or a C, drain cavity. Normally, when we go to large projects, they always want to do an A and a B, because it's easily controlled, easily designed, and everything else. But when you look at other standards in TfL, particularly my standard in drainage, it requires, if you don't have drainage on a structure, you have to put drainage in. So the cavity drain behaves as one of those requirements. So the C-type drainage basically behaves as one of those requirements. So I'll go in a bit more detail exactly what that is in a couple of slides. So the table for different waterproofing requirements is out of 8102 is what's grade 3, what's grade 2, and what's grade 1. So you can read up there. Grade 1 is generally for car parking. Grade 3 is about well-ventilated domestic areas, commercial areas, and so on. It's very different. It changed in 2009 from the old standard. The old standard had grade 4 as well, which was more aimed at domestic and libraries and so on. They changed that and moved everything back to grade 3. So that table, when we follow it, doesn't say that we have to have 2 types of waterproofing. It only says we need to basically work to this performance requirement. So quite regularly when we talk to our construction teams and whatever, they think we're working purely and simply to this table and going to do 1 layer of waterproofing which guarantees the waterproofing of that structure. In practice, what we have found over history, we've got 155 years of buried structures, 1 type of waterproofing doesn't work. Yeah? It fails. You know, certainly in the lifespan of that. So when we're designing objects, obviously we design for 120 years for most of our civil structures, quite quickly over the period of 20 or 30 years in, contractors left site, everyone's gone, contractors probably changed a few times, names and everything else. We have leaks with single basically waterproofing types. So we rewrote our standards to basically look at how we control that, and that's 2 types of waterproofing. So, different types of waterproofing, different systems out there. So when we talk about type A, type B and type C, type A, there's under the tables there's different types, but type A is like a membrane system, and you can put a membrane down through a wall, seal it to a wall. You'll see some photographs in a minute of different systems out there. Type B is type A, that's a type A, so it's about waterproofing, putting a membrane either internally, externally. Personally, I prefer an external membrane in some ways, because then when the water pressure's on, it's pushing it against the wall. So you're using the natural physics to hold it in place. Internal membranes, they're just as good, and they're easier to apply. Contractors generally like to use an internal because it's easier to construct with your temporary works and other environments, and potentially less likely to get damaged. They vary in size. Type B, Waterproof concrete, designed to a minimum crack width. We make sure we can put additives in, whatever else. There's lots of detailing issues with waterproofing concrete. And I'll show you some defects in a minute on 9 Elms, which is a recent project we've been doing a lot of work on. Obviously, construction joints and expansion joints all need detailing, all need understanding how they're going to behave. And you have to look at that not just from a structural point of view, but also a waterproofing point of view. And fundamentally, people forget the waterproofing until the end, and they just put some hydrophilic strips in. Not really adequate. The last one is a drain cavity. Type C, drain cavity, so that sort of shows you the drain comes down and it connects through to the floor, gets taken off to a pump. Quite regularly on underground we put these in, they're dry for a few years, we spring a leak somewhere, or someone goes and drills a hole in one of our walls, it leaks, and then we basically our cavity receives water. And that's what it's there for, it's to protect, it's a second line of protection. Very, very useful. So, in the underground, lots of examples of large basement constructions were going on in the last few years. Obviously, we've had the Crossrail projects going through where we've built large, significant basements. And how do we construct those? When we start looking at the construction of basements, particularly, we're understanding different construction methodologies. So, construction methodology, do we go open cut, top down, and bottom up? There's lots of choices there, and there's lots of ways and understanding and issues with each type of construction. So we need to understand those when we're detailing, not just from a structural point of view, but also a waterproofing point of view. Because in the waterproofing, if you get it wrong, it basically leaks, and it gives us a long-term problem. Now that is 9 Elms. Yes, that is 9 Elms in the background there, and you can see some of the leaks already coming through from that construction. That's a water-barred concrete system. So, no, it's not 9 Elms, can't remember what that is. Gravity drainage, so retaining walls. So we have to choose how we're supporting our walls during our basement construction. Do we look at gravity? Do we look at embedded walls? There's lots of different reasons for choosing each, different ground conditions, different environments, different water level issues, and so on. So we make choices, but in that, we also have to understand the behaviour and the movement of water into those structures. So, how are we supporting our walls? So, supporting our walls, are we going to put temporary props through? Are we going to basically make it so large it doesn't need it? Ground anchors, berms, or are we going to put permanent slabs and props through to basically take that load during the construction and temporary works and the long-term support of that wall? Lots of decisions that have impacts and details around those that need to be understood and waterproofed to prevent water ingress. The problem is, and I went down to Connaught Tunnel as a good example of that. Connaught Tunnel, during the construction of Crossrail, existing tunnel, lots of work around Connaught Tunnel. Water ingress was an issue on Connaught Tunnel and still is an issue. The design was already exceeded by the time they lifted it, and then they told me they hadn't actually removed the dewatering. So Connaught Tunnel was a problem because as soon as we moved the dewatering, the flow went up even further. Only by a few litres a second, it wouldn't get much higher, but that already exceeded the design was for 120 years, not the design that we required at the beginning. So where does water enter structures? There's loads, during construction, there's loads of entry points of water. So when you start looking at how we build things, and that's why it's so important to work out in your structure how you're going to build it, because how are you going to stop water entering it? So at the top, you've got surface water. Does it enter through the structure? And how do you design that? Do you build your capping beam slightly proud, and therefore providing passive, but you then got the connection between the flooring and whatever else? How are you preventing that migration of water through there? Predominantly surface water isn't a major problem. We can put drainage in the surface to allow it to drain. Capping beam connection and actually wailing beam connection actually is our biggest problem at the moment, because the detail below the wailing beams and below the capping is where we don't get good compaction on our concretes and our mixes as they go in, and therefore that connection doesn't work and doesn't waterproof very well. They also don't detail it with modern water bars. Well, I'll show you some details of that. Water directly through the wall. I'll show you some good details of that later. Walls dropped the thing there, I noticed. But when we have to design our walls, what wall type are we using? How are we waterproofing that? If we use a secant pile system, with that secant pile, how are we designing it and how are we speccing that secant pile wall? But actually, if we're using that as one of our primary methods, we don't accept that in underground, but some people do, of waterproofing, it generally leaks. Now, how are you correcting those leaks before you go to the next stage of works? Next one is we get water through the base and up from 4. So it comes through the piles underneath, below our structure, and then up, and it follows the path of 6. Below the piles, so does it flow? So do we key in our piles deeper and take more and increase the flow path? There's lots of detail around that. The joint between the basement slab and the wall is critical as well, understanding how we do that joint. Normally that's in quite difficult construction conditions. It's hard to basically prepare the sides of those walls, and contractors prefer not to. The slab thickness obviously helps. The thicker the slab, obviously the more likely it is to be better at waterproofing. Through the slab is also a problem. At 9 Elms we've had problems on all of these points, so we'll go through them. So, let's just talk about surface water. Obviously, TfL, we see loads of surface water incidents of flooding. Now, that's actually an existing station up on Metline, which is, which station was that? Sorry? It's not Ruislip Manor. No, I haven't got a good photograph of Ruislip Manor, which is about 1.5 meters deep. It's, I can't remember, it's actually where the track goes above this one as well. Where cars are floating. That's just on Brexit Day, actually. What do we do? We've got, for surface water, there's lots of options. We can obviously put surface drainage in. We can work with drainage around that area. Obviously, we're driving towards sustainable drainage. We can design that relatively simply. So, from an engineering principles of that waterproofing, it's pretty easy to remove that water and give us the protection that we require for it. The next one is looking at construction joints in the main structure. So as we go down, so there's lots of examples of poor construction joints. Not all of these are 9 Elms, but some of them are. The top bit is where the capping beam goes through, top right-hand corner is where the capping beam goes through, and we have probably 15 or 20 sites on that site where, because of the construction joint between the capping beam on the secant piling system, it leaks like a sieve, and it's cost us a small fortune on looking at this. Now, 9 Elms is an interesting site because we picked this up in design, and we said, we're not particularly happy with this, but people at TfL had valued engineered out the cavity system. So originally, in the reference design, we had a secant pile wall, we had a liner wall with a membrane in it, and then we had a cavity drainage system. They then went through the design process. We did a review, said, hang on, where's our cavity drainage gone? And they said, well, we value engineered it. We're building a watertight structure. We're going to use waterproof concrete, and we're going to use a lining wall. And we're going to use a nice solid liner all the way through. It won't leak. And I said, my experience is everything leaks. So we've got to start with that. Under S1052, which is the gravity standard that I manage, it says if you don't have this, you need cavity drain, you need to put drainage in. They valued engineered that out as well. They saved themselves £200,000 by value engineering that out. It's cost us at the moment nearly 300 grand in rectification work, and we still have a structure that leaks. It just doesn't leak as badly as before, and I'll go on to that in a minute. So, construction joints leaking, lots of examples. That's the Northern Line tunnel, where the blind end comes in. It's leaking under the tunnel, so how do we correct that and what do we do? One of the construction joints, that's not a 9 Elms, but they used hydrophilic strips that were fixed about a week and a half at 9 Elms before the pour. And hydrophilic strips exposed to the elements for a week and a half, they react, they don't work, we cast onto them, and then we have leaky joints. They also had re-injectable grout tubes, which is these things here, you can just see the box. Because of the poor formwork situation at 9 Elms, we lost a lot of those boxes and had to hack the wall back to find those. When we got to it, a lot of those re-injectable points didn't actually work, and we couldn't re-inject through them, and therefore we couldn't seal, so we ended up drilling holes everywhere to basically seal it. Looking at how we should have done this, and we tried to encourage the contracts to work, was looking at traditional construction joints with water bars, so plastic water bars. Hydrophilic strips, I don't class as water bars. They're something, if you can't use a water bar, you're binding onto an existing surface. You can't cut a water bar in very effectively, so then you can use a hydrophilic strip, but you would look at an alternative measure as well. It's only one thing. But if you're going to put hydrophilic strips in, you're going to, you need to do them just before the pour, and you need to fix them with, as per the manufacturer's instructions. So what they've done, they've Hilti nailed them to the concrete. So actually where they've Hilti nailed it, it couldn't expand. So that gave it a straight flow path, and so on and so on. Bottom corner is how they were sealing. So they've got down here, you can see the hydrophilic strips down the bottom, the red thing. The green one is the re-injectable grout tubes. And then you've got the lining wall on the back. So that's the liner, and then the lining wall itself, the waterproof concrete lining wall was going in the front of that. The main issue we've got was how they did the formwork for this. So the formwork for this structure, and I think I'll come on to that in a couple of slides actually, is looking at basically how they cast it up against it. So how they put that lining wall in was critical as well. So the next one, let's just talk about walls and floors. So that's the floor on 9 Elms. Now it's rather deceiving. That was after a long dry spell. So this was slightly open to the elements. Long dry spell, and some of the walls were leaking. But when we got the walls mostly dried out, the floor was still leaking. So it was coming up through the joints in the floor, because the construction joints on those floor joints weren't prepared properly before they cast, and they didn't once again use any form of water bar or any system. And they hadn't looked at putting any sort of drain cavity in the floor. Since then, 9 Elms, all construction joints have now had like a delta membrane put through to basically control that flow of water and manage that flow. The secant piling system, we had loads of leaks around the secant piling system. It was meant to stop all water. When we got to it, these piles I think are 30 metres down at that point. So they go about 45 metres into the ground, 50 metres into the ground. The tolerance of these piles, by the time they got there, they hadn't basically met their tolerances. And actually the male and female piles that they basically had driven hadn't meshed together very well, and we had numerous leaks. So what did we do? We ended up having to grout, a large amount of grout to try and seal that, because we can't put our liner on that wall. One, because it's wet and it won't bond very well. Second of all, the water pressure, every time we put the liner on, it pushed the liner off. So, learning point from that, get your secant piling wall, get your specification right, and make sure your contractors are going to work and basically make those tolerances work. And if they can't work, come up with an alternative waterproofing system. So, I sort of mentioned earlier about the different systems for doing the formwork. So, one of the problems we had at 9 Elms is they designed a cheaper formwork to basically hold and cast the lining wall through a letterbox opening at the top. That formwork was installed using divvy-dag and held in place using divvy-dag bars through the waterproofing membrane. So it went through the waterproofing membrane. They did a lovely job of epoxy sealing around that divvy-dag point and everything else, but a large number of them still leaked. So we put a lovely bit of crack width waterproof concrete up there, and it's still at the divvy-dag points leaked like a sieve. And we had about 30 or 40 locations where we had minor leaks, and we had about 10 locations which leaked like a sieve and ended up having to be regrouted. But it doesn't mean that the divvy-dag point's leaking as a point. So you don't just drill out the divvy-dag point and refill it, because actually that didn't solve the problem, because it wasn't necessarily the divvy-dag put at that location. It was to do with when they backfilled it, how well they filled it. So what did we change after basement level 1 at the 9 Elms? We looked and asked them to look at a cantilevered system to prevent them having to do a number of holes. You still have to do the odd hole through the waterproof lining just to hold that formwork in place, but it was less than 10% of the holes they were proposing going through your nice brand spanking new liner. So with that, we limited the number of holes and perforations through that liner by changing that. Now, I sort of spoke about the next bit, which is the piling specification. So Damp patches. We reviewed our piling spec, and we would like to move to in future. This was what was used at 9 Elms, but driving that is difficult. Don't rely on secant piles to hold water back, because it doesn't work very well, especially in variable ground. We had loads of problems driving those piles at 9 Elms. The environment and the ground conditions, we end up with sinkholes on site and all sorts of issues associated with those piles. And because of that, we ended up with a lot of water ingress through those piles. So the piling spec, which they used, still applicable, and you still want to use that. Don't rely on it as a waterproofing system. It's okay for construction side, and it's probably okay for a grade 1 start off before you put something on, but it's not good enough in the long term. So we're talking about different flow routes, water main and sewerage. So when we're assessing what flows are coming through, we need to understand where that water starts. So certainly in our tunnel sections, our existing tunnels, we have a large amount of different sources of water originally. So we need to understand, where does it start, what is it? So is it water main? Is it sewage? Is it surface water? And how do we control that? So we have a list of parameters. They're not perfect for everywhere, that assess what type of effluent inflow you're getting, and therefore you know how to treat it. So groundwater, surface water, we treat those subtly different. Surface water we can maybe drain and manage in a different way. Sewerage, don't really want to try and grout sewerage, because it probably means grouting up the main that you're nearby, and that's a gravity system. Water mains, less of an issue, but you have to have a consideration on where it is. There are many different types of grout we use. So we try and avoid using grout these days, because actually it's very expensive and it doesn't work very well. We can spend millions of pounds grouting tunnels, and we have done in the past, and actually not have the desired effect. But there are four real types of grout: cementitious, epoxy, polyurethanes and acrylic. And they all have their different reasons for use. So when you look at cementitious, structural grouts, and basically applying those in different areas, we have to choose that area depending on where we are. Epoxy, once again, linked slightly to the cementitious. Do we use those in structural areas, crack repairs and so on? Polyurethanes, large void, lightweight, high expansive grouts. Have to be careful with those near water, because sometimes they expand out of control. That's what happened on the Bakerloo line in 2012, I think it was, where we popped the tunnel lining using polyurethane trouts. And then the tunnel lining then interfaced with the train on the first train through in the morning. And then we had to shut the tunnel while we cut the tunnel out and repaired the tunnel. Acrylics, so different acrylic grouts, generally used where we generally use those with another grout. They're very fine, they're very viscous, very easy to get through small cracks. But you wouldn't use this on a large hole, because one, it's very expensive. Second of all, it just flows off everywhere and you lose it. But you have to know and understand what you're grouting and prevent grouting up things around the area that you don't want to grout. So, we did once grout the BT tunnel over near Mansion House, because we drilled the hole, we put our grout packers on, we jacked them up, put them to about 2,000 psi, pumped lots of grout. After 1,000 litres of grout, we couldn't work out how it went down such a small hole. And we then realised we'd drilled a hole through into the tunnel below when we basically put them a new floor in their tunnel. So be aware of where you're grouting, and understand that. We found it because we put a bamboo cane up with a little rag up, and we walked down the tunnel and there was a bamboo cane sticking up. So be aware of that, understand what you're grouting, understand the pressure. So when we're dealing with old structures and new structures, but old structures in particular, especially brick line tunnels, understand that you can't just grout them the same as you can cast iron tunnels or concrete tunnels. We need to understand that. You need to measure that while you grout. But you have to have a long-term game in management, because you're not grouting to stop the water, you're grouting to push the water somewhere else. So
to grout to too high a pressure, you're probably not going to stop the water, you're probably going to cause more damage, and you could push it somewhere where you can't control it. So you could push it to somewhere, try and push it to the knees of the tunnel, or try and push it to somewhere where you have active drainage already. There are also loads of different additives and pore blocking systems we can use. We've got render linings and so on. We've also used electrolysis systems where we put mesh. So over at Walthamstow, we have a system, an EPS system, where we've got a mesh over the tunnel, and that then has an electric current, anode and cathode, and that holds the water out. Very expensive to install, works really well, relatively low maintenance costs, but it's a bit prohibitive because you can't do very much of your structure, because as soon as you break that ring, it starts to leak. It used to leak like a sieve before 2007 when it was installed. We don't get any water down there at the moment, and that's basically been updated a few times, but we have to be very careful around that structure, because if we move it, do anything with it, we have to make sure that continuity of that material is still there. Excellent. Final slide. So the gist of today is talking about supplying drainage systems, understanding how you're maintaining different environments and managing water, not controlling it. Don't drill holes in structures to grout them without understanding where you're grouting to. Sometimes you're forced to do it. 9 Elms, we've had to do extensive volumes of grouting to try and prevent that. The other big site we had loads of problems not far from here, Tottenham Court Road. Tottenham Court Road is very similar. They valued engineered out the drainage system before construction. They constructed it, and then we spent nearly £2.5 million grouting elements of that to try and stop water. And if anyone remembers when Tottenham Court Road first opened on the first day, it shut, the new section of the station shut about 3 hours into operation because of a leak coming in on a construction joint directly above the escalators, which if we designed it properly, worked with the design properly, we wouldn't have had that problem. Excellent. Bit of a whistle wind tour, but if anyone's got any questions?
So we've got a microphone here, so if anyone's got any questions, just so that for the purposes of the live stream, so that everyone can hear. Sure, we've got some questions.
Go on, someone be brave.
Oh, Nick.
So one of the most forms of gravity I came across I think using the square, because platforms were leaking down, people wondering what was going on. So we wandered down that way to have a look why the wall was leaking, and find it being grouted up, and it was actually a cavity wall.
Yep.
Grouted up the cavity.
Yeah, we've had numerous, so where we've got cavity drainage, once again, understand what you're grouting, look at your records, don't grout up our cavity drainage. But also, we've had the opposite, where you've gone into a machine room next to it, because we've got water ingress. We've grouted there, it's migrated 4 or 5 metres round, and then filled the cavity wall as well. So understand, and that's where your pressure's really important, because if you're putting too high a pressure through on your grout lines, and where you're measuring it, if you're measuring it back at the compressor unit, that's useless. You've got to measure it at the wall and where the point of injection is, because your losses through your machines and everything else. Or you at least have to understand what you're doing and where it's migrating to.
One of the things about this is keeping your asset records up to scratch.
Yeah.
If you do grouting, you need to know where you've done it, what you put in. Otherwise, you get the same problem with Baker tunnel, where previous grouting was actually the problem, not the grouting they were doing.
Yeah.
But also, you have an understanding as to how you're working. One of the other things about cavity walls is if you don't leave any room for maintenance, it will plug up anyway, so you must get some means of access.
Yeah, so we're looking at numerous new projects at the moment. So Leighton's a new one where we're looking to go between the 2 tunnels, dropping a new box in. We're looking at cavity, and you need access to those cavities, one, to be able to get inspection of it and to clean it. So they don't have to be particularly big, as long as you can get a rod to it. But, you know, anything more than 10, 15 metres is pretty ineffective with a rod. Now, you can put robots down to clean them and whatever else, but it all adds to expense, adds to time. So actually more inspection holes, it's better in some ways to let it basically come down the wall and inspect it as it comes in, just have a drainage system in locations. Obviously it's not particularly architectural in those locations. Now bear in mind that 9 Elms is meant to be raw concrete architectural finish. when we get to the end. So it'll be interesting to see what condition it is. And on those sites, obviously, they're meant to be lasting 120 years. Luckily, most of the leaks at Nine Elms at the moment are back of house areas, so we can deal with them as we need. Any more questions? Go on.
As you've seen, it's quite a common occurrence for you to be caught off guard with a leak. So how do you manage the flow of passengers so that you have enough space to work on that leak and for it not to be too detrimental for their journey?
So obviously the main aim of TfL is to move people around London. It's not to do engineering works. So the aim is, first of all, manage the project and design things that don't leak. When they do leak, we end up having to isolate areas. That causes a lot of disruption, and it's one of the problems we've got. So it's all about good design practice, good construction practice, and preventing it in the first place. Obviously, where we don't have significant leaks. With flooding, if we have flood risks and so on, we have management plans in place to allow for that. We generally have time. Obviously, water mains we don't, but we're doing a large project looking at water main flooding at the moment. But management of passenger flows, we have our evacuation plans. We know, and our station staff are all trained to deal with people, to get people around the station in the most efficient way. Obviously, fire risk in LU, so our fire plans. So actually, if we end up shutting lengths of tunnel, it can mean closing the whole station while we do that works. Yep. So electrical equipment rooms, they really dislike water in electrical equipment rooms. Signal rooms, they really dislike water. And therefore, they're priority areas. So they're where we may grout, but we'll push it to a room next door where we can deal with it. And the normal way of dealing with it, if we have a leak, is physically pipe it and manage it into the location where we can put it into a drainage system. So quite regularly, we'll drill a hole and force it to that hole to drive it out. So electrical equipment rooms and SCRs, signal equipment rooms, are always sensitive to water. So with those, they're priority for us, and putting a lining skin in there quite regularly, you haven't got the room to do that.
A couple of questions from me, if I may. First of all, climate change. Yeah. Given that the UK projections currently go to 2080, and you're building new infrastructure with 120-year design life, what are you doing about climate change for the life of those new structures? And the second question is, what are you doing about long-term changes in groundwater levels?
So let's deal with one at a time. So obviously, climate change, we design on the EA guidance. So for flows, we're increasing those by 40%, and we've been doing that before. 2016, February, we were doing 30%. But we also look at the resilience of our structures, and we understand those. So when you're looking at portals, tunnels, signal equipment rooms, electrical rooms, we're designing them for a 1 in 200 year event, where most of our track environments we're designing on a 1 in 50 and so on. So it's about resilience. We aren't going to design everything to resist water and other issues. And some of our track, to lose a track for a day while we have a storm, yes, it's an inconvenience, but actually to design it to the level of requirement potentially in 100 years is financially just not available. The other question was
Long-term changes in groundwater levels.
So long-term changes in groundwater. So the Guardit Review 1999-2000, we obviously still work with Guardit. We are having problems with Guardit now, and some of the people who are stakeholders in Guardit, and them not wanting to manage certain areas of level of water in the aquifers and the deep aquifers. At the moment, it isn't impacting our stations. We aren't seeing significant more pump systems pumping more flows out. But it is something that's on the radar. It's on one of our risks. It's something we're assessing under our flood risk review. And obviously with our waterproofing, we generally design all our structures to groundwater to where they would reach in in an event as well. So we would drive, basically, normally it's up to nigh on ground level. Certainly with Battersea and Nine Elms being near the Thames, it's nearly to ground level with that design. If not, it is to ground level. So all our waterproofing structures are to there. But we are aware, certainly in the Battersea area, groundwater is on the rise. Groundwater rise is quite slow in comparison. You know, you're talking half metres per year, if that. So it is slow, so we do have time to react. And the main solution is we'll end up having to pump more out. So ensuring we've got correctly sized pumps and ensuring the risers and the other infrastructure is in place for it. But it is a problem that's there, and we'd like to keep our guarded levels and our agreements in place.
You sort of mentioned it in the last answer, but with Cyclone Sandy in the States, in New York, there was a cascade of problems, and quite often it was the pumps failing, or the electrical system or something else. Is there a system where TfL can manage those types of risks?
So when you look at Sandy, yeah, they had a problem with the pumps more being overwhelmed rather than failing, which then wiped out the panels. It was just the sheer volumes of water they received. Our pumps standard is pretty good. I was involved in writing it. And our spec is pretty, we work more on a resilience on spec rather than technologically. So we have a SCADA system which links to it as well, but we have control. So we have full SCADA control. So we can control our pumps from anywhere in the world, and we can therefore switch pumps. We obviously run with duty pumps where we need. So if you look in this area, probably the largest pump in this area is at Victoria, where we're pumping 130 odd litres out a second out of that well. And we've got 3 pumps in there, all on that sort of duty. And the idea is if one fails, we've got 3 resilience. We've got 2 power supplies at least to those locations. Our panels themselves are not complex. We deliberately stay away from PLCs. We deliberately stay away from transformers. Electrically, people don't particularly like not having transforming down to 24 volts because they say it's not safe, but only competent staff are allowed into our transformers. So we control the risk that way. But if you're going to have a failure in a panel, it's generally going to be around a transformer failure rather than another component. Also, you can't divert round transformers. You can through the systems we use. So we have backup systems for that. It doesn't completely resolve the problem because we still end up with large volumes of water potentially entering the underground. So the last one that actually happened was 2012, Old Ford vent shaft. Thames Water popped a water main just up the road, and someone opened the door and let all the water into the vent shaft, and they couldn't close the door because of the sheer flow. We ended up with just over 3 million litres of water on the underground. Stopped us for 27 hours on the Central Line. Now, Central Line, Jubilee Line are our most expensive lines to stop for any length of time. Just before the Olympics, a little bit embarrassing. That wiped out the panel of the pump. So it wasn't the panel, the water actually fell on top of the panel as it came through. So it wiped it out because it wasn't seen as a route of water entry in it. So that's one thing in our design. We are considering a placement of panels and critical infrastructure around our network and trying to ensure that water doesn't affect those.
Any more questions?
Thank you, Anthony. You mentioned that some of the TfL infrastructure is over 155 years old, and obviously a lot of the LU infrastructure is now upgraded in a piecemeal fashion where old meets new. Do you think that any preventative future waterproofing measures can be 100% effective, or will there always be a need for drip trays?
I think there's always, I've gone on, management is there. So drip trays is management. So even new infrastructure leaks. So yes, drip trays are there. So in your design, you should be designing to put drip trays in, even if it doesn't leak. Because actually space allocation for drip trays are allowing us to put them in 50 years' time. Because at some stage, those structures will leak. So yes, and where old meets new structure, always leaks. From my experience, nigh on impossible. If it leaked before, it will leak again, and it will leak at that location. And that's exactly what happens at Tottenham Court Road, where the new infrastructure met the old, it leaked. Where we had cast iron rings going into concrete, it still leaks. And square works going into tunnel bore works also leak. It all has a problem because it's a break in the continuity of that structure. So in those areas, they should be designed with adequate space allocation to allow for drip trays or other systems to allow them to be drained.
So following on from lessons learned from the Battersea site, what's being put in place going forward to actually learn from the lessons that we've seen from that site and other sites like Tottenham Court Road you talked about?
So the main lessons learnt really from Nine Elms and places of that nature is one, getting the right people in the room to make value engineering decisions. And I'd like to say it's a lessons learned. I don't think we've learnt that yet, and we still fail that point. We don't get the right people in the room making the decision. It's very project manager led on value engineering and not technically led. So the drive is to move more technical, get the right people to make that decision. And it shouldn't be around just money. Quality is so important, especially when you're designing something for 150 years or 120 years. Because actually, if we've got to pump water out of Nine Elms for 120 years, 200 grand was infinitesimally small compared to the cost of that pumping over that time step.
Fantastic. Anything else? Oh, well, we've got one more. Making me run tonight.
Something that I found interesting was the use of exterior membranes for waterproofing concrete, and with increasing water levels and thus increasing water pressure, do you think this will act, although it might be quite expensive, do you think it will act as like a means of waterproofing concrete throughout the rise in water pressure?
So obviously, if you have an external membrane, it pushes against the wall, and therefore it hasn't got anywhere to go. So if the water rises, it's a more effective way of doing it. If you design it on your internal membrane and it's leaking, that pressure pushes on it. So you've got to design that really to the full potential head of water. And the problem is people generally don't want to do that. They want to design it for what they see or what they envisage. So there is more risk associated with that. Normally with the internal membrane, we put a facing wall in, which will be a concrete wall or something of that nature on the front, which will prevent some of that movement. But it doesn't mean that that waterproofing is still adequate with the movement because it may degrade over time. And obviously moving part, so if it does have freedom to move, so membranes that are allowed in a gap don't work as effectively.
Great. Well, I'd just like to thank Anthony for coming in this evening and giving us a talk. If everyone could give him a round of applause.
Thank you very much.
Just want to do a few plugs for Engineers Australia while I've got all your attention. We've got quite a few activities coming up in the next couple of months that we wanted you to be aware of. So we've got the summer barbecue coming up on the 18th of August. So that's going to be down at the Oval. It's going to be whilst we've got the county match running. So that's Hampshire versus Surrey. It'll be from 11 a.m. So if you're interested, there should be an advert coming out on Eventbrite in the next week or so. It's live already, brilliant. So hopefully we'll see a few of your faces there. So we've also got a site visit coming up for Nine Elms. Now that you've heard all about it, you probably want to see it. So Luke's busy organising that for us at the moment.
Yeah, so that's the 11th of September. Invites on Eventbrite will go out in the next week. It's limited spaces and ideally BYO PPE, sorry for the acronyms, but if you don't have access to protective gear, just give
sort of long-term horizon, we've got the Christmas soiree that's being hosted by Engineers New Zealand, which is on 22nd of November. So again, hopefully we'll have a good turnout there and enjoyable evening. We've got our AGM coming up on the 8th of October. So again, hopefully we'll see a few of you there. Try and get a good bunch. We've had a really good committee this year, and Ben, who wasn't able to stick around, has been doing an excellent job in the president position, Rob in the treasurer, so hopefully we can get a few more people to take up some more active roles in the committee. We've got a possible underground tour through the London Transport Museum coming up. We're going to try around about November. I'm not sure which station, disused section of the station we're going to go down to at the moment, but it'll be for about 22 places, I think. And the next Getting Chartered event will be in the third week of September. I'm also trying to get us a tour out at Small Satellite Technology out in Guildford, so hopefully they'll get back in touch with me. And for those of you that didn't hear about our regional trip that we just came back on last month, we went out to Cologne, a bunch of 10 of us went to the European Space Agency, got to meet Andrea Boyd, who is actually looking after her first launch as flight controller for the next crew of 3 going up to the International Space Station. You should be able to catch some of that live on the NASA live or ISS live streams that are through either YouTube or the internet. They're quite easy to get hold of. But next year we're trying to get a regional tour off the ground over to Flanders, the Western Front, to follow in the footsteps of tunnellers and engineers from Engineers Australia, Engineers New Zealand, from the First World War. So we'll go out to the Manning Gate, we'll go see the tunnels at Amiens, and go down to Bretano and see the big Australian New Zealand memorial down there, and the new Sir John Monash museum that's gone in. So lots of things coming up, and hopefully we'll get to see a few of you there. But thanks very much for your attention. And, yeah.